with a radius of 30 centimeters creates a real image 45 centimeters from the mirror. What is the object distance? So go ahead and try this one. And keep in mind, I said this earlier. For a lens or a mirror, the focal length is equal to the radius divided by 2. So if that's a little hint, you need to get started on this. Go for it. Alright, so let me explain this. We can draw it again, just for the sake of understanding. So we have a concave mirror. A concave mirror looks something like this. And so the object is here. Light rays come in, and they reflect off of it and create this image over here. And it's going to be a real image, but it's going to be inverted. So we can have the focal length of the mirror, we can have the distance of the object, and the distance of the image. The focal length in this case is, they give us the radius. So if we divide that by 2, we get 15. They say that the image is 45 centimeters from the mirror. You need to really pay attention to what they're saying. It creates the real image that is 45 centimeters from the mirror. That means that di, which is distance from image, is 45 centimeters. And you know that di is positive because they tell you it's a real image, right? If they said a virtual image, you'd put negative 45. And so we're supposed to solve for distance from the object. So they're asking object distance. That's the only one we don't know. So the equation on this is the same for everything. Mirrors and lenses is combined. So focal length is 15 centimeters. Distance from the image is 45 centimeters, and distance from the object is unknown. So if we solve for the distance from object, we're going to get .5 centimeters. Give me a moment to make sure this is correct, because I don't quite remember it being this. I've done these a lot of times. Let's see. No, that's right. Okay, good. All right. Question number 7. A substance has an index of refraction of 1.46. Light leaves into air at an angle of 53 degrees. At what angle will light pass inside the medium? So go ahead and try this. And again, remember this equation if you need it to solve this. Okay. So we have a situation where the substance is an index of refraction of 1.46. So substance that is entering has 1.46. Light leaves into air at an angle of 53. So light is starting in air, and air again is always 1 for the index of refraction. So we have our little interface between the two mediums, and we have the angle of, or the normal line really. Okay. So then this creates a little light ray that comes in. So they're saying that it leaves into air at an angle of 53 degrees. So this angle of incidence, or what did I just write? Angle of incidence, the I should be smaller, equals 53 degrees. At what angle will it pass inside the medium? So to do this, it'll be, since the index of refraction is more than 1, it's going to be bended a little bit. It's going to bend this light ray. We're going to get this angle of refraction, and that's what we're trying to solve for, right? They're saying at what angle will it pass inside the medium, which is not air. It's the thing that has a 1.46 index of refraction. So to substitute these values into this equation, N1 is for air, that's just 1. And then sine of the angle of incidence, which is 53 degrees. And then we have 1.46 for the index of refraction of the substance. And we have sine of the angle of refraction. All right. So we get 33.16 degrees. All right. So this question is asked about a vertical plane mirror. What a vertical plane mirror is, so we had these concave mirrors, right? We had these convex mirrors, concave, convex, but we can also have mirrors that is just like vertical plane, right? A plane mirror. What a plane mirror is, we had a convex mirror, we had, a certain radius, which meant we have a certain focal length. In this case, this just doesn't have any focal length. Excuse me. The concept of focal length really doesn't apply here, because this, if you extend this out, right, it wouldn't turn into a circle. However, mathematically, when we use the equation like this, it actually makes sense to treat the focal length of this as being infinity. So this had a focal length of something positive. This had something negative, but the focal length here is equal to infinity. And so this 1 over f is going to be, when we have vertical plane mirrors, is going to be 1 over, let's draw it a little bit higher up. Right, it's going to be, this is irritating. It's going to be 1 over, my goodness, all right, come on, 1 over infinity. Whenever you have 1 over infinity, you have 0. So this side is 0. All right. What that means is you have this. When you have this, it basically turns into negative 1 over di equals 1 over do. Right? So what that means is, and you can flip this, right? So make it to negative di equals do. Whenever you have a vertical plane mirror, this is the situation. It's always going to create, you're always going to have a distance from the object, and then it's going to create this virtual image that's exactly the same distance from the mirror. So it says, how far are you from your image when you stand 0.75 meters in front of a vertical plane mirror? So what we're doing is, we have a mirror, and we're standing as a person 0.75 meters from it. So this is 0.75 meters. And the distance, our image is going to be exactly the same distance from it, right? It's going to be 0.75. In this case, since it's a virtual image, right, it's negative, it's going to be an upright image. So when you look inside a mirror, this is probably what you see, right? You see yourself, and you perceive yourself as being the same distance as you are from the mirror. So now they're not asking you how far your image is from the mirror, right? They're not asking for this 0.75. They're actually asking how far are you from your image, right? So how far are you from your image? So they're asking for this distance. And if you look at the diagram we drew, it's 0.75 plus 0.75, which is 1.5 meters. That's one way to think about it. Another way to think about it is just using mathematics, right? This equation here, if your distance from the mirror, your distance from object is 75, well then the di is just going to be negative 75, right? So di would be negative 75. And if you add the quantities, forget the fact that this is negative, just add 75 plus 75, you should get 150. Or 1 point, sorry. You should get 150 centimeters, but 1.5 meters. An object is 15 millimeters in front of a converging lens, and the image is 4 millimeters behind the lens. So then they're asking, what is the focal length of the lens? So a converging lens would look like this. So the object is here, and the light rays come in, and they converge. So they come in and converge, and they, was not good. Okay. And the image ends up being inverted. Now, the distance from the distance of the object, they say it's 15 millimeters in front of a converging lens. This is 15 millimeters, and the image, which is over here, distance of that is going to be 4 millimeters. So they're asking what is the focal length. So again, the equation. Again, the reason I draw these diagrams is not because you need to draw them every time, but just to reinforce the conceptual understanding of it. So if you solve for this, focal length is going to be 3.158 millimeters. Okay, go ahead and try this problem. You could probably do it. A light ray in air is incident on air to glass interface at an angle of 50 degrees and is refracted at an angle of 25 to the normal. What is the index of refraction of the glass? So we have air on top, right? We have glass on bottom. So the index of refraction of this is always going to be 1. And we're asking for the index of refraction of the glass. So we have the little normal angle. Then we have the light ray is incident on air to glass interface at an angle of 50 degrees. So the air to glass interface is here, and we're going from air to glass, and the angle of that is 50. So this is the angle of incidence, is that, and then we have the light, it gets bent a little bit, so then now it's a slightly lower angle. Well, not slightly, in this case, it's actually angle of refraction is 25 degrees. So then if we use Snell's law again, which is this equation, where the index of refraction of the substance the light is coming from, times sine of the angle of incidence is equal to the index of refraction of the substance the light is going into, times the sine of the angle of refraction, right? In this case 25. And this n is what we're solving for, and this was 1. I should have put 1. So if you solve for this second index of refraction, you're going to get 1.8126. So that's your answer. This next question asks, what is the speed of light in diamond if the index of refraction of diamond is 2.42? So there's a relationship here that's important to understand. Light doesn't change its frequency, but it can change its wavelength depending on what substance it is in. So the equation for this is that the index of refraction of the substance is equal to c, and c is the speed of light, right, in vacuum. So c is speed of light in a vacuum where there's no molecules around. There's nothing, right? And then v here is the speed of light in the medium that we're talking about. So the medium can be like glass, water, oil, air, whatever. So the relationship you can see, so c is always going to be 3 times 10 to the 8 meters per second. It's really like 2.998, but it doesn't matter, right? And then v is the speed of light in a specific substance. What you notice is there's a certain implication. For air, we said the n is basically 1. It's not really 1, it's close to it, but it's close enough that we can just round. So what you can notice is that the speed of light in air is almost exactly the same as the speed of light in a vacuum. So air does not interfere with the speed of light at all. Okay. But notice the relationship. The higher this number goes, the lower this number has to be. So the higher the index of refraction, the more we're going to impede the speed of light. So that's how you should conceptualize it. In this case, they say the index of refraction of diamond is 2.42. So n is 2.42. It's a pretty high n. That means this v should be pretty small relative to the actual speed of light. So we solve for the speed of light in diamond. We get from this v is equal to 1.2397 times 10 to the 8th meters per second. So that's the speed of light in diamond. It's a lot slower than the speed of light in vacuum or in air, right? Because the index of refraction of diamond is high. So here we have it says the critical angle for plastic material is found to be 50 degrees. What is the index of refraction? So here's what the critical angle means. Imagine we have again an interface between an interface between two materials. So we have air, and then we have in this case plastic. In this case, we have a normal angle. as we always do. Now, if the light comes in from air, right, the index of refraction in plastic is higher. So this angle of incidence is going to be turned into the angle of refraction. And it's actually going to be smaller. So this angle of refraction is a little smaller. Right? But imagine we had the opposite scenario. Imagine we had, let's draw another scenario. We never considered this situation before, where the light is actually coming in from the plastic itself into the air. Right? So that we're going to have the angle of incidence. But in this case, since the index of refraction air is higher, or actually, sorry, index of refraction is lower than plastic, right? Because this n is basically 1. The n here is bigger than 1, right? This angle is actually going to increase. Right? It's going to increase. Or that should be r, right? Refraction. Let's delete this right side or left side scenario. We don't need it anymore. Okay. Now, something interesting can happen. In some cases, when the angle is just right and when the index of refraction is just right, what can happen is that this light ray can come in and hit the substance. It's coming in from a high index of refraction substance like plastic, water, oil, diamond, as we learned about, and coming into a low index of refraction substance. Generally, these questions are going to be air, right? So it's coming in from plastic into air at a certain angle. But then, if it were to go straight, it would go like this. But it's going to bend it a little bit, so it's going to go like this. In some cases, it'll bend it so much to the point where it'll actually go like this, where it'll be perfectly parallel to the interface between the two surfaces. In that case, the angle of refraction is equal to 90 degrees. Okay? This situation is called total internal reflection. Okay? It's when the angle of refraction equals 90. And so if we look at our equation for this, it would mean that N1, and then we have N1 in this case is the substance that we're coming out of. In this case, it's actually going to be the index of refraction of plastic, right? So this is N1, and this is N2 of air. N1 times sine of angle of incidence, right? And then we have N2. And N2, in this case, is the index of refraction of the air. And then sine of the angle of refraction. If we plug the values we have in this situation into this equation, we'll get something interesting. Okay, so N1, which is plastic, we don't know. We're trying to solve for it because they're saying what is the index of refraction of the plastic material. Sine of angle of incidence, and then N2, which is 1, which is for air, and then sine of 90. And you might wonder, we have two things in here, so what happens? Okay. If you read the question again, the critical angle for a plastic material is found to be 50 degrees. The critical angle is the angle of incidence, right, at which the angle of reflection is 90 degrees. Okay, that's what the critical angle means. So this is 50. So once again, critical angle is what is the angle of incidence when the angle of refraction is 90. That will be the critical angle. And it's always coming out of the high index of refraction substance, like plastic, water, oil, and into a lower index of refraction substance like air. So generally for critical angle, assume that the substance outside is air and the substance inside is whatever they're telling you. In this case, plastic. And then assume that the the light is actually coming from the plastic into the air for critical angle problems. So this is actually 50. So if that's 50, we can solve for the index of refraction of the plastic. And this is how the index of refraction of a lot of the material is found. Right? You can theoretically find it using the speed of light, but that's not, you can't measure that, right? With this, you can get a pretty good measurement. So the index of refraction of this plastic is 1.3. All right. Next question says, a particular lens has a focal length of 10 centimeters. How far from the lens should an object be located in order to produce an erect image that is 5 times as tall as the object? When it says an erect image, it means that it's upright, so it's not inverted. So it says that the focal length of the lens is 10 centimeters, and it says specifically positive 10, right? That's on purpose. So if you remember, what type of lens would have a positive focal length? It would be a converging lens, right? So like this. And we have an object, and they're saying that the focal length of the lens is, I mean, it's kind of useless, but anyway, is 10 centimeters. And so we're trying to get the light through this lens. Let's actually put the little thing closer. And these light rays get under the same point, and we get an inverted image. They're trying to make an erect image, so this wouldn't work, right? Sometimes what a converging lens can do is actually bend light this way. And the cases where it does that, you kind of don't need to know really, but it's only when the object is really close to the lens. So when it's like the object is closer to the lens than its focal length. So in the equation, it's written like this. We have the focal length, the distance from the image, distance from object. So the focal length is 10. The distance from the image, and the thing we don't really know, right? But what we do know is this ratio that we talked about earlier, about height of the image and height of the object and negative distance of the image to distance of the object. We're trying to make an image that is 5 times as tall as the object. So meaning the image is 5 times as tall. So negative di over do, if the image is 5 times as tall as the object, this should be 5. And specifically, the image should be, the image should be upright. And we realize that upright images are in this equation are positive. And actually, this should be height because we're talking about height. Right? So if that must be 5, then we put 5 here. So we have we can multiply both sides by do, and then we can multiply both sides by -1. There. So distance from the image is negative 5 do. So as opposed to di, we can put we can multiply both sides of this one by 5. So the 1 becomes a 5 on top. Multiply this one by 5. And we can make this right side negative, so we can say negative 5 and negative 5 over here. So now we have a common denominator, we can add those up. So that'll be negative 4, negative 5 over do. And then we can solve for do, which is so the distance from the object is 8 centimeters. Okay? And they're asking for how far from the lens should the object be placed. So distance from object, this is the answer. So in this situation, an object is located 20 centimeters in front of a spherical mirror with a focal length of 10 centimeters and positive 10 centimeters specifically. Where is the image formed? So the spherical mirror has a focal length of plus 10. That means it must be a concave mirror. So the light comes in, hits the mirror, and then the image is formed back here because the light reflects from it, and then we get this inverted image. That is a real image. Okay. So in this case, the focal length of the mirror is a value. They give us is 10. Distance of the object from the lens, or from the mirror in this case, is 20 centimeters, and I'm asking for where the image is. So distance of the image. Distance of the image is 20 centimeters. It's 20 centimeters. Does that make any sense? Yeah, so this should be right here. Right? It should be drawn differently, but distance of the image is 20 centimeters. Same as the object. So I hope that helped you understand these problems. Have a good day.